Now that we have our chi-squared result, we can start proving confidence interval results for our coefficients. So beta hat, and if you don't know this already, if we haven't gone over this, it's x transpose x inverse x transpose y. Under the assumption that y is normal x beta sigma squared I, show that expected value of beta hat is beta, and that the variance of beta hat is equal to x transpose x inverse sigma squared. And this should be old hat to you by now. I want to point out one comment though, as is normal, what we saw in linear regression, that it's really variability in the x's make our variance in our coefficients smaller. It's because of that inverse there. So just like before, you want to increase the variability in your regressors to decrease the variance in the standard error of the coefficients. And that makes sense. If we have a linear regression and our estimate of the line is going to be much more variable if we only measure the dots in a really tiny variance of x. But if we spread them out all along a very wide variance of the axis, then we'll get a less variable estimate of the line. Okay, so small extra point going on there. The other point I'd like to make is that the covariance of beta hat and E is 0. And I can say this because the covariance of beta hat and E is the covariance of x transpose x inverse x transpose y, and the covariance of E is I minus h of x and y. Okay, so that's equal to x transpose x inverse x transpose covariance of y with itself and I minus h of x when I pull it out on the other side. Covariance of y with itself is sigma squared I, so this works out to be x transpose x inverse x transpose times I minus h of x times sigma squared. And then we know that if we multiply this matrix times x transpose, we're going to get 0. So the covariance of beta hat and E is 0, and then because of the normality, that means that beta hat and our residuals are unrelated. And so similarly, our y hat and our residuals are unrelated. We've seen that they're orthogonal, but now we actually see that they're statistically unrelated. There we go. Okay. Now, let's prove our t-distribution result for our coefficients. So take some linear contrast of the betas. Let's say Q transpose beta is a linear contrast where Q transpose is Q is a p by 1 vector, and Q transpose beta then is some contrast of the betas that we're interested in. So as a simple example, Q might be equal to, say, 0, 1, 0, 0, 0, and then Q transpose beta would just pick off the second component of the beta vector. Or, this contrast would pick off every component of the beta vector, but often we might be interested in the difference between two coefficients and so on. So our natural estimate of Q transpose beta is Q transpose beta hat. So Q transpose beta hat is clearly normally distributed with mean Q beta and variance Q transpose x inverse Q sigma squared. Furthermore, since beta hat is independent of the residuals, Q transpose beta hat will be independent of the residuals, hence they'll be independent of any function of the residuals, so they're going to be independent of s squared and any function of s squared. Okay, so Q transpose beta hat minus Q transpose beta divided by square root Q transpose x inverse Q times sigma squared is going to be normal 0, 1. Furthermore, we could divide this whole thing now. We could divide this whole thing by the square root of n minus p s squared over sigma squared, which is, the denominator is the square root of a chi-squared divided by its degrees of freedom. Oh, I'm sorry. I want to divide by an extra n minus p there, which is the square root of a chi-squared divided by its degrees of freedom. So this quantity right here we've talked about as chi-squared, and there is its degrees of freedom. So work all these together, and I'm just going to move over here. I get that q transpose beta hat minus q transpose beta divided by s square root q transpose x inverse q is exactly a normal 0, 1 divided by a chi-squared divided by its degrees of freedom, where the top and the bottom are independent. So this is a t-distribution with n minus p degrees of freedom. So it is exactly using this result that we get that the individual coefficients from our linear model follow a t-distribution, and then this is exactly how we get that the individual coefficients, that we get the t-table for the individual coefficients, for example, in R when you do summary. Okay, so let's go through a coding example of this, but this is exactly where the results in that t-table come from.